Welcome back to Mr. Vaughn's classroom. Before we get started, I'd like to ask you to please hit the subscribe button and give this video a thumbs up. Today we're looking at Unit 5, Introduction to Exponential Functions, and we are on Lesson 11, Modeling Exponential Behavior. Our learning goal today is to use exponential functions to model real-life situations. We have two learning targets today. As we work through the practice problems, keep these two learning targets in the back of your mind, and at the end of the lesson, we'll come back and we'll look at these and make sure that you know exactly what you're supposed to have learned in this lesson. Learning target number 1 says I can use exponential functions to model situations that involve exponential growth or decay. Learning target number 2 says when given data, I can determine an appropriate model for the situation described by the data. And we have one glossary term in this lesson, and that is exponential function. An exponential function is a function that has a constant growth factor. Another way to say this is that it grows by equal factors over equal intervals. For example, f of x equals 2 times 3 to the power of x defines an exponential function. Anytime x increases by 1, f of x increases by a factor of 3. This simply means you're multiplying by the same number over and over again. In this case, you're multiplying by 3 each time. Now we can begin on the Unit 5 Lesson 11 practice problems. Here is an image showing the highest point of the path of a ball after one bounce. Someone is collecting data to model the bounce height of this ball after each bounce. Which measurement for the location of the top of the ball would be the best one to record? So, a couple of things that you may need to know in order to solve this. First, you can estimate one measurement beyond what is marked. And what I mean by that is the markings, the smallest marking, you know for sure what your measurement is related to the marking that is actually there. And then you can estimate a little bit beyond that, so in between the two markings. The next thing that you need to know in order to solve this is that each numbered line is a centimeter. Each smaller line is 1/10 of a centimeter. So we know that the top of the ball is right here. We know that that is above the 26, but below the 27. So we know that the 26 is correct in each of these choices. The next thing we see are these millimeter lines that represent 1/10. So if you count 1, 2, 3, 4, we could even go as far as to say 26.4 is known. So we're going to mark A as incorrect. And then we know that it's somewhere between the 26.4 and 26.5, so we can actually estimate to one more place. So we would say that answer C is the most correct and as far as we can estimate. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any clarification that I can offer. Next practice problem says function h describes the height of a ball in inches after n bounces and is defined by the equation h of n equals 120 times 4 over 5 to the power of n. Question number 1, what is h of 3? What does it represent in this situation? So first, to solve it, all we need to do is substitute 3 into the equation for n. Now, 4 over 5 equals 0.8 when you put it in a calculator. So this becomes 120 times 0.8 to the power of 3, which is 0.512. Now when we multiply that by 120, we get our final answer of 61.44. Next, they want to know what it represents in this situation. Well, 3 is inside parentheses, and that would make it n. N is the number of bounces, so that would mean 3 bounces. The function itself is telling us the height. So this tells us the height of the ball after 3 bounces is 61.44 inches. Number 2. Could h of n be 150? Explain how you know. Well, what I know is that 120 is the initial height. I know that 4 over 5 is my growth factor. And I know that I'm multiplying by a growth factor of less than 1. So if I'm multiplying by less than 1 each time, my number can only get smaller. So the answer here is no, because the height starts at 120 inches and gets smaller because it's always multiplied by less than 1. Number 3. Which ball loses its height more quickly? This ball or a tennis ball whose height in inches after n bounces is modeled by the function f, where f of n equals 50 times 5 over 9 to the power of n. If we want to know which ball loses its height more quickly, we need to compare their growth factors. So when I look at this new equation, this time I see that the growth factor is 5 over 9. And we already said 4 over 5 equals 0.8. Now we need to see what 5 over 9 equals. 5 divided by 9 equals 0.5. We'll round at 6. So 0.56. This means the tennis ball loses height quicker because its growth factor is smaller. .56 is less than 0.80. And question number 4, how many bounces would it take before the ball bounces less than 12 inches from the surface? So what we can do is we can start out with the 120 times 0.8. So we can start at h of 3 since we did that one on number 1. So we know that h of 3 equals 61.44. So let's start at that. So 0.8 to the power of 3 times 120. So here we are at h of 3 bounces. Now let's multiply by 0.8. So that means h of 4, we're down to 49.2. So we're not there yet. Now let's multiply this by 0.8. And that means after 5 bounces, we are down to 39.3. Let's try a 6th bounce. Multiply by 0.8. We're down to 31.5. So let's go for a 7th bounce. We're down to 25.2. Let's go for an 8th bounce. Multiply again by 0.8. We're down to 20.1. Let's go for a 9th bounce. Multiply by 0.8. We're down to 16.1. Let's go for a 10th bounce. Multiply by 0.8 again. We're down to 12.9. We're almost there. So let's try an 11th bounce. Multiply by 0.8 again. And we're finally down to 10.3. So it would take 11 bounces before the height was less than 12 inches from the ground. If you have any questions about how to solve any part of this practice problem, please leave a comment below and I'll get back to you with any assistance I can provide. Our third practice problem: after its second bounce, a ball reached a height of 80 centimeters. The rebound factor for the ball was 0.7. From approximately what height in centimeters was the ball dropped? So, let's fill in what we do know. We know that the height is going to equal 80 centimeters. They're asking us to find the height in centimeters the ball was dropped from. Well, that would be our initial amount, and we usually call that A. Then we need our growth factor. Well, they tell us right here the rebound factor for the ball was 0.7. That is the growth factor. And now we need to know what the exponent is. Well, they're telling us it's the second bounce. So that means our exponent is 2. So the first thing we can do is go ahead and do 0.7 to the power of 2. And 0.7 times 0.7 is 0.49. Now, we have A times 0.49. We want A by itself, so the opposite of multiplying is dividing. And we're going to divide both sides by 0.49. When we do this, anything divided by itself becomes 1. So we just have a times 1 on the right, and that becomes a. And then on the left, we have 80 divided by 0.49. And if we round this, the 2 tells us to keep this at 163. And that matches answer D. Now, logically, you could have eliminated A and B just because you know we could not have dropped a ball from 34 centimeters or 49 centimeters had it bounced twice with a growth factor less than 1 and end up with a higher bounce on that second bounce. So A and B could have been done logically. Then it would have come down to C and D. But if you just fill in the information that they give you into the exponential equation, then you can just isolate the unknown, which is the starting height, and solve for A. If you have any questions about how to solve this practice problem, please leave a comment below, and I'll get back to you with any clarification I can offer. Our next practice problem gives us a table of values on the right and asks us which equation is most appropriate for modeling this data. So, the first thing we need to notice is that right here we have x equals 1 and y equals 79. This is not the initial amount. This is the amount when x is 1, not when x is 0. So right now, I know that it can't be choice B, and I know that it can't be choice C, because they both say that the starting amount is 79. So now the only question is, are we multiplying by 1.25 each time, or are we adding 22 each time? Well, if we were adding, then 64 plus 22 equals 86, and 86 does not equal 79. So this would not be the proper amount to add each time. Now we can look at A. If I take 64 and I multiply that by 1.25, then we get 80. And 80 is a lot closer to 79 than 86 is. What if we tried it again? What if we said 1.25 squared times 64? Well, that would put us at 100, and the table said we'd be at 101. Again, we're only one off. So this choice is a lot closer to being correct than any of the other choices. The reason that we might be off by 1 could be a slight estimation error or a slight rounding error when they originally set this up. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any assistance that I can offer. Our last practice problem says the table shows the number of employees and number of active customer accounts for some different marketing companies. The question they ask is, would a linear or exponential model for the relationship between the number of employees and number of customers be more appropriate? Explain how you know. So they're not saying that it's going to fit exactly. They're asking which one is more appropriate. So a couple of things we need to understand first. Linear is when you're adding the same amount each time. Exponential is when you multiply by the same amount each time. So, if we look, we're adding 1 each time when we start out here. So down at the bottom, we can see that we add 4 to go from 4 to 8. We add 5 to go from 8 to 13. And we add 4 again to go from 13 to 17. So every time we increase x by 1, we add about 4 or 5 each time. Then what we can look at is, what are we multiplying by each time? Well, to go from 4 to 8, we would multiply by 2. But if I multiplied by 2 again, I would get 16, not 13. So to see what I really multiplied by, let me take 13 and divide it by 8. And I find out I was multiplying by 1.6. Then, to find out what I multiply by to go from 13 to 17, I can take 17, divide it by 13, and I find out I only multiplied by 1.3. So if I was going to say one of these fit better, I believe it looks more consistently to say that we're adding about the same amount each time rather than we're multiplying by the same amount each time. So for my answer, I would say a linear model would be more appropriate. Because we're closer to adding the same amount each time than we are multiplying by the same amount. Each time. So be sure to understand that the difference between a linear equation and an exponential equation is that a linear equation is adding the same amount each time, whereas an exponential equation is multiplying by the same amount each time. Before we finish this lesson, I want to go back and review the learning targets and make sure that you understand what you needed to for this lesson. So here we can review the learning targets. Number 1 says I can use exponential functions to model situations that involve exponential growth or decay. Simply remember that an exponential function takes the initial amount and it multiplies it by a growth factor, and that growth factor is to the power of the input. The input tells you how many times to multiply that initial amount times the growth factor. And learning target number 2, when given data, I can determine an appropriate model for the situation described by the data. This simply means if you look at the data, you understand that a linear model is when you're adding the same amount each time. An exponential model is when you're multiplying by the same amount each time, and you can determine which one is more appropriate for that situation based on the data. I hope this lesson was helpful to you. If you did find it helpful, please hit the subscribe button and give this video a thumbs up. I look forward to seeing you in the next lesson.